Welcome back to differential equations. This is day 2, lecture 1. We will be covering sections 2.1 and 2.2 today. So to begin with, we want to talk about direction fields. We've talked about direction fields before in either Calc BC, Calc 1, or Calc 2, depending on where you were at before. But we can consider a direction field given by dy dx is equal to x. Now, our ability to solve this direction field or solve this differential equation is irrelevant to what we're going to do right now. We're going to draw a grid, and since any differentiable function is locally linear, that means that we can get an idea about the shape of the solution to this differential equation by looking at the grouping of all of the possible tangent lines. Now, there are an infinite number of numbers that we could be plugging in here. We're not going to plug in an infinite number of numbers. We're just going to plug in convenient numbers for us. The goal here is to get an idea about the shape. So if I plug in the point 1, 1 to this, at 1, 1, the slope of the tangent line, remember, which is equal to the derivative, in this case is just the x value, which is 1. So at the point 1, 1, we have a slope of 1. At the point 2, 1, then our slope is 2. Our slope is equal to the derivative. The derivative is equal to the x value. So at 2, 1, we have a slope of 2. At negative 1, 1, we have a slope of negative 1. And at any x value of 0, we have a slope of 0. Any x value of 1 gives us a slope of 1. Any x value of 2 gives us a slope of 2. Any x value of negative 1 gives us a slope of negative 1. So this gives us an idea about what the solution curves to this differential equation look like. We can imagine if I started, say, here, then the equation itself might look something like that. But we could also start here, and we would still have an idea about what the solution curve looks like here. We could have the differential equation that dy dx is equal to the sine of y. Same treatment, right? We look at our coordinate plane, plug in different values for x and different values for y. At, say, x equals, say we have the point 1, let's do 1 pi over 2. And then that'll just be my step size. At 1 pi over 2, the slope is equal to the sine of pi over 2. And as we all know, the sine of pi over 2 is 1. So at this point, we have a slope of 1. At the point 1 pi, we have a slope of the sine of pi, which is 0. So here we have a slope of 0. And in fact, anytime the y value is pi, we have a slope of 0. Anytime the y value is 0, we have a slope of 0. Anytime the y value is 3 pi over 2. Our slope is the sine of 3 pi over 2, which is -1. So here we have a slope of -1. And that's true for any of those y values. Filling this out with a couple more points, the sine of negative pi over 2 is -1. And so we get a much different direction field or slope field than we had before. But we can say, well, if you start in the middle here, your solution curve is going to kind of look like that, kind of look like a logistic equation. And if you start up here, your solution might look like that. So again, the whole point here is we can get an idea about the shape of the solution to the differential equation, which follows the described behavior. We could have dy dx is equal to xy. In this case, our slope is always equal to the product of x and y. So if I have the point 1, 1, I have a slope of 1. At 2, 2, we have a slope of 4. At 2, 1, we have a slope of 2. Any x value of 0 or a y value of 0 is going to have a slope of 0. If x is -1 and y is -1, those multiply to get +1. If x is 1 and y is -1, those multiply to get a slope of -1, and the same for reverse. And then -2. At 2, -1, our product is -2. And at 1, -2. So we could keep going through these points. And we could draw what we believe a solution curve to this might look like. If we start up here, maybe we look kind of like a quadratic, but without solving it, who knows? So let's have some definitions now. We last time defined some classifications of differential equations. We classified them as ordinary or partial. We defined them as first order, second order, third order, and so on. And we defined them as linear or nonlinear. We're going to add a definition to that. If you have an ordinary differential equation, which does not have an explicit independent variable in the equation, is said to be autonomous. And so if we write our differential equation in the way that we saw last time, where if this is the first order, then dy dx is equal to f of xy. In this case, x does not appear, so we could just simplify this to be f of y alone. So in the previous 3 examples, the independent variable here is x, and I see x on the right-hand side, so this is not autonomous. In this second equation, the independent variable is x, and I don't see it on the right-hand side, so this is autonomous. And in this one, the independent variable is x, and I see x on the right-hand side, so this is also not autonomous. All right, next definition. A value c is said to be a critical point of a differential equation if f of xy is equal to 0. At C. Now, this definition leaves a little bit to be desired right now because we have x and y defined here. We have c defined here. In calculus, we defined a value x equals c to be the location of a critical point if f of x equals 0. And to be clear, when I say f of x, I mean the right-hand side of the differential equation. But if our differential equation is autonomous, then we don't have f of x, we have f of y. So in this case, we would need to say a value y equals c is a critical point if f of y equals 0 at y equals c. Now, this actually comports very nicely with our definition of critical point from calculus because calculus tells us that we have a critical point anywhere the derivative is 0. And here we're just literally saying the derivative is 0. It might happen at an x value. It might happen at a y value. But either way, if the derivative is 0, then it's a critical point. This is also called an equilibrium point. And it's also called a stationary point at this stage. So these are terms you might hear used interchangeably with a critical point. Okay, let's remind ourselves that if the derivative is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. Those were theorems that are consequences of Rolle's theorem, the mean value theorem, etc., from calculus. All right, so let's look at a differential equation. Let's look at a first order differential equation. dp dt is equal to p times a minus b p. Perhaps this causes us some consternation because of the choice of variable names and the fact that there are parameters here. So we'll look at a specific member of this form that might look like a dy dt is equal to y times 3 minus y. So here I've replaced the dependent variable p with the dependent variable y, and I've let the parameter b be equal to 1 and the parameter a be equal to 3. And so we end up with this differential equation. Now, if we want to discuss the behavior of this differential equation, we can talk about this in terms of its slope field or direction field. And if I plug in values here, what we might notice about the right-hand side of this differential equation, based on the definitions we just saw, is the independent variable here is t, but there's no t on the right-hand side. This is autonomous, which means that any of our slopes are going to be the same for any t value. So let's plug in a couple at the 0.11. Our slope is 1 times 2, so our slope is 2. If y is 0, our slope is 0. And if our y value is 3, our slope is 0. If our y value is 2, this is 2 times 1, slope of 2 again. If y is -1, then we have -1 times 4, which is -4. It's a very steep negative. So we get a direction field that looks something like this, and so we might guess that the solution to this might look something like that. But what I really want to emphasize here is t is irrelevant to the slopes. All we need to tell you information about this from is the y value specifically. So I could redraw this just talking about the y value and remove the t value from consideration entirely. So all I've got is this vertical line, and the numbers I care about on this vertical line, well, the equilibrium points are the spots where this equals 0. That happens when y is 0 or when y is 3. So if I mark these here at y equals 0 and y equals 3, this now should feel very familiar because we did this in calculus when we were talking about finding critical points and the behavior of the function between those critical points. Well, for any y value between 0 and 3, I'm going to have a positive number times a positive number, so my slopes are going to be positive. So we could say in general, any value in this region is going to result in increasing behavior. That's what we saw here. It's going to increase to 3. If I plug in a number bigger than 3, gives us, let's say 4. 4 times a -1, which is a negative number. And in fact, for any number bigger than 3, I've got a positive times a negative, which is going to be negative. So I can include that information in my drawing. For any value bigger than 3, I'm going to have decreasing behavior, right? I could plug in the 0.14 here, and I would get that this is decreasing. And so any solution here might look something like that. And for any value less than 0, say -1, I get negative times 4, which is -4. In fact, any value less than 0 is going to be a negative times positive, which is negative. So I can tell you that if I start with a value less than 0, I'm going to be decreasing. And we see that if we draw a solution curve for this as well. The cool impact of this, the importance of this is I don't have to solve this differential equation to tell you the behavior, the long-term behavior of the system. If you tell me if you start with a y value of 1, I don't have to solve this. I can just tell you, you start with a y value of 1, that's between 0 and 3. Your function is going to increase to 3. And I don't have to solve it. I don't have to solve that differential equation. So this is incredibly powerful. We might compare this to something like dy dt is equal to y minus 1 squared. Again, we can make the slope field for this, but observing that this is an autonomous differential equation, there's no t on the right-hand side. That means that we don't need the horizontal axis in our slope field. In fact, all we really need are the important values here, the spots where the derivative is 0, the equilibrium points. Well, the only spot that makes this equal to 0 is y equals 1. So on my sort of stylistic slope field, if you will, I'm going to include this value, y equals 1. And now let's see what happens if I give a y value less than 1 and a y value greater than 1. A y value less than 1, say 0, is going to be -1 quantity squared, which is positive. So if I start with a y value less than 1, all solutions must increase to a y value of 1. And if I start with a higher y value, say 2, above y equals 1, 2 minus 1 is 1, 1 squared is 1, that's positive, and so this function is going to increase as well. So what we have is a very succinct way to describe the behavior of this function. Because it's autonomous, I don't need to know the t value. I can focus on just the y value. And now if you tell me, oh, I've got an equation or something I'm modeling that has this behavior, this dy dt is equal to y minus 1 quantity squared, and I'm starting with a y value of 3, well, I can tell you, given a y value of 3, your function is going to continue increasing, and since there's nothing up above here to stop it, it's going to increase without bound. If you tell me you start with a y value of 0.5, I can tell you it's going to increase to 1. So we see there are actually 3 different types of points here. It's possible that all of the arrows point to Rome, or this equilibrium point. It's possible that the arrows point away from the equilibrium point, and it's possible that the arrows don't change behavior. It'd be nice if we had classifications for these, like in calculus, we would describe a critical point as being a minimum or a maximum. Well, we do. All solutions around this value that start in the neighborhood of 3, if you will, approach 3. So that means this is called a sink. Or an attractor. It's also called stable. It's a sink or an attractor because solutions are pulled or near it are pulled toward it, and it's stable because if you start at 3 and you perturb the solution just a little bit, it goes back to 3. Now this one, our arrows are pointing away. So this is a source or a repeller. It is also called unstable. We call it a source or a repeller because if you start around 0, you're going to just move away. You're going to be repelled by it. It's also called unstable because if you start at 0 and perturb the solution just a little bit, it's never going to come back to 0. Now, this one where they didn't change, we call this semi-stable. It's half stable, right? If you start down here, it's going to approach 1. That's stable behavior. But if you start up here, you're going to go away from 1. That's unstable behavior. So we see that we have a couple of different classifications we can make for these equilibrium points. We can classify them as a sink or an attractor, unstable, or a source or a repeller, or unstable, or we can classify it as semi-stable. All right, that will be the end of this lecture. I'll see you in a couple minutes probably for the next one.